Hello, welcome to another problem session. This is a very good problem from this book. I highly recommend this book. So you want to check it out. The problem is that a man is on a cart here. You can call it car, which is going around. And this is some kind of track or rail track, and it's rounding a bend with a constant speed, so it will be like a circular motion. If you're interested in the center of mass motion, there's a center of mass over there. So if you're interested in center of mass motion, that's the cm. Cm is a height L from the ground, not necessarily half the height of the person, is somewhere here. This is given. And track, this end of the track is a distance r from the, if you think of a cm is going in a circle. At this moment it will be a circle like that. That will be distance d. The legs are apart like this, so it's above that. So this will be like r plus d over 2. That's the circle that's going in. But the question is not about the cm motion. Instead, the question is about how much weight is on each feet. Thing we want to know is actually if there's a normal from at this feet is straight up, and then there's a normal at this feet is straight up. So we want to know these two. So n inside, the leg that's inside, let's call it n1, and n that's outside, let's call it n2. So those are the two forces we want to know. That's so the question is about find magnitudes n1 and n2 in the figure. So that's what we need to find. Well, clearly, if we think in terms of just motion itself, so motion of center of mass. So if I just look at the center of mass motion, so translational motion of center of mass, this would be based on external forces. So if I look at it, acceleration is that way of the cm. So this is the acceleration of the center of mass in that direction. So there must be some force in that direction. So if you look at the forces, this is not in that direction. There's actually on this feet, there must be a friction F1 in that direction, and on this feet similarly there is a friction F2 in that direction. So these two are the only forces in the direction of center of mass, acceleration of center of mass. So that will be like F1 plus F2, and these are static friction and not necessarily maximum. So we don't know what this relationship is with the normal. So this is equal to m v square over, I got r, so the radius of the circle is going in r plus d over 2, right in the middle. Separation distance between the feet is d. So we can say r plus d over 2. So that's one equation. but I don't know what F and N's are related, so it's actually, we are stuck here. Another thing you can notice it is if I look at the vertical direction, forces on the C vertical direction, so this one is weight, which is not along the track but vertically down. So, and the normals are vertically up. These are vertically up into an N1. So from there, and there's no acceleration equal to 0 along this axis. So we will get N1 plus N2 equal to mg from those three forces. But we need something else to find N1 and N2. Okay, so we can't say that torques are balanced, etc. But actually, if I let me redraw this picture a little bit for clarity. Okay, so I redraw this picture over here. I redraw this picture. So here is this essential parts only. So here's the CM, weight acts on that, and you have the normal forces and the frictional forces acting on these points. Okay, if you look at the V is coming out, and from this axis is actually coming out. The RCM is coming out. So if I look at angular momentum around this, it's actually not changing. So notice DLCM, so axis about x to CM dt is actually 0. That means tau about this axis equal to 0. So if all the external net, so you want to talk about it. So if I look at it, there's a weight is actually going through the CM. So tau weight will be 0. How about the tau of N1? N1 is going this way and N2 is going that way. So N2 is counterclockwise and N1 is clockwise. So let's take a counterclockwise positive and clockwise negative. So tau N2 is plus N2 times this of, if you go up there, the distance from this axis, that is just d over 2, and tau of N1 is minus, because it's going to be clockwise, so minus N1 d over 2, and then tau of F1 is, F1 and F2 is going to be the same distance, so and it's going to be this way clockwise, so minus F1 times this distance is L. From here, if I drop onto the axis for the F's acting, that distance is just L, and tau of F2 is minus F1 L. And so all of this added up is 0. So I'll say N2 minus N1. So N2 minus N1 is F1 plus F2. F2 N2 minus N1 is F1 plus this F2 2L over D. All right. So this is the third equation. And if I put it in here, let's call it the right hand side. Let's call it R. Just whole thing as R. Everything is known. We're just going to call script R. So this is equal to 2L over D script R. So using 3' and 2, if you add it, N2 will go away. So I mean N1 will go away and N2 will be so from 2 and 3', you should get N2 equals 2 of these equal to R plus the this divided to 1 over 2 1 plus 2L over D. So R is common. It's going to be like this. So, and N1, you can subtract this guy from it. So R over 2, 1 minus 2L over D. And R is just this big mess. So R is this big mess. And you can put this there. So that's the answer. So let's go over just one more time. This is a really lot of things going on in this problem. We had to take into account the translation motion, and these are the friction forces, and they're not they're static, but not necessarily F maxes. So we don't know what the relationship between F's and I can't do mu and things like that here, okay? And they're not given anyway. And second is these are normal forces. These are the weights, basically weight on each will push down and the normal is a reaction to that. So this is equal to the weight that pushing down. And then we had to notice that tau has to be about this axis has to be 0. Now if I took an axis like that and we had to on one of the legs, you'll have to actually convince yourself whether L is not changing around this or not. So each one of these you have to actually make sure you have a good case for your L changing or not. But for center of mass, we can make an argument very directly that because center of mass RCM cross VCM, this will be the L, it will be M. So this is about this is of the CM. When you look at this quantity will not be changing with time, and the torque will be fixed as at 0. Once you get this condition, then we just implement those torques, and we have to be very clear, sure about various signs. So if we had a clockwise, we had a minus, and counterclockwise we had a plus. And after that, it was easy to see that this we didn't need to know this. We just replaced this by the right hand side here, which comes from uniform circular motion. This came from uniform circular motion. Okay, so that's all. I'll see you in another video. Talk to you later. Bye.